Good morning, everyone. Welcome to Guru Brahma classes for JEE and NEET. Today's topic is quantum mechanical model of an atom and its important features. Right? So, in this, let us see. From Heisenberg uncertainty principle, we have studied that it is not possible to calculate the position and velocity of an electron accurately at the same time. And from that Heisenberg uncertainty principle, we have studied that there is no possibility for a trajectory. There is no path around the nucleus. And the concept of probability has been came into existence. So from Heisenberg uncertainty principle, we have studied that there will be only probability of finding electron around the nucleus, but there is no trajectory or a definite path around the nucleus. See here in quantum mechanics or quantum mechanical model of an atom from classical mechanics, which is based on Newton's laws of motion. So classical mechanics ignores classical mechanics did not take the concept of dual nature of matter. So based on classical mechanics, it is proposed that the movement of the particle, so matter is having only particle nature, but matter is not having a dual nature, that is wave nature. So classical mechanics takes only the particle nature of matter, but wave nature of matter is not taken. But whereas in quantum mechanics, the motion of microscopic objects that have both wave-like and particle-like properties are explained, are discussed in quantum mechanics. So quantum mechanics deals with both particle nature and wave nature. So wave nature of the matter, that means wave nature of microscopic objects is taken into the consideration. So quantum mechanics is individually developed by two scientists named Schrodinger and Heisenberg. Right? So what is that fundamental equation in quantum mechanics? That fundamental equation was developed by whom? Named Schrodinger or Schrodinger. So what is the Schrodinger equation? See, Schrodinger wave equation. What is that equation? Schrodinger wave equation describes the wave motion of an electron. Already we have studied that from de Broglie wave nature of an electron not only possesses particle nature but also possesses wave nature. That wave nature or wave motion of an electron is described in this Schrodinger wave equation. Wave motion of an electron is described in Schrodinger wave equation. So Schrodinger wave equation describes about a three-dimensional concept of moving electron. So moving electron, its wave nature is explained and its three-dimensional movement is also explained. Or three-dimensional motion is also explained in a Schrodinger wave equation. So this equation is based on de Broglie wave equation as well as Heisenberg uncertainty principle. So what is that equation? See, this is the equation, looking to be somewhat larger. So the details of this equation, the derivations of this equation is not in our syllabus. In your higher classes, you will learn about it, but simply what is this equation? What are the quantities present in this equation? Only up to that we have in our syllabus. So Schrodinger wave equation is a differential equation of second order. So differential equation of second order. You know what is meant by differentiation? So it is written as, what is that? Del square. So what is this called as? This is called as what? How do we represent del? Simply if you write this one, it is called as d. D. If you write this one, this is called as delta. So what is this? Del. Del square psi by del x square plus del square psi by del y square plus del square psi by del z square plus 8 pi square m by h square e minus v psi is equal to 0. So this is the equation. Okay. So what is del? Del is partial differentiation. What is this? This is partial differentiation. What are this x, y and z? X, y and z, if you see here, see these x, y, z are coordinates of an electron with respect to nucleus. So consider this the center as nucleus. This is a nucleus, right? 0, 0. This is considered a nucleus. Now an electron is moving. Okay. Electron somewhere here, the electron is. This is electron. So the position of this electron with respect to x-axis, the position of electron with respect to y-axis, and the position of electron with respect to z-axis. So these x, y, z represents the coordinates of electron with respect to nucleus. With respect to nucleus, what are the coordinates of electron? What are the coordinates of electron? So those are called as what? X, y and z. The remaining things, h is Planck's constant. So in the formula we have h. So what is this h? Planck's constant. We have v. V means potential energy of the electron. E means total energy of the electron. M is mass of the electron. Okay. And what is psi? What is this called as psi? P silent. We call it as psi. Psi means it is a wave function. We call it as a wave function. Or simply we can also call it as amplitude. Called also amplitude. So for example, amplitude of a wave. Let us take a transverse wave. Electron motion is also like a wave. So if you consider a transverse wave, let us take a transverse wave. Okay. Let us consider a transverse wave. So this is transverse. In a transverse wave, there will be successive crust trough. What is this? This is called as a crust. Crust trough. So the maximum displacement of the particle from the mean position, and this is called as a psi or amplitude. In considering a transverse wave, it is having two parts. One is called as negative part, this is positive part, and we consider this as negative part. Okay. One is a positive part, another is a negative part. So psi can be positive or psi can be negative. So psi means amplitude of a wave, or it is also called as a wave function. So that is called as what? Psi. So one way of representing this Schrodinger wave equation is del square psi by del x square plus del square psi by del y square plus del square psi by del z square plus 8 pi square m by h square into E minus V psi is equal to 0. Okay. That is about a Schrodinger wave equation. Schrodinger wave equation, why we are mentioning it as wave equation? Because it describes the wave motion of an electron three-dimensionally. This Schrodinger wave equation takes both de Broglie wave equation and uncertainty principle into the consideration. Okay. Next, Schrodinger wave equation can also be represented by, in another way, it can also be represented. What is that? Del what is that? This is also called as del square. It is also called as a del square. Del square psi plus 8 pi square m by h square E minus V psi is equal to 0. How do we call it as? We call it as del square. What is this del square? Del square is a mathematical operator, like what is that called as? Laplacian operator. Laplacian operator. So this operator, what is Laplacian operator, how it is used, and all these things are out of our syllabus. Simply remembering these things is in our syllabus. It's one type of mathematical operator. But mathematical operator means in mathematics we study plus, minus, negative, divided by, into. All those are mathematical operators. In that way, it is also one of the mathematical operator, which is called as a Laplacian operator. So in this way also we can represent a Schrodinger wave equation. So where del square can be dou square by dou x square, del square by del x square, del square by del y square, plus del square psi by del z square. This will be del square. Okay. Next, for a system such as an atom or a molecule whose energy does not change with the time, Schrodinger equation can also be represented as h psi is equal to E psi. H cap psi is equal to E psi. So where this h cap is called is a mathematical operator, which is also called as a Hamiltonian operator. It is also one of the mathematical operator called as a Hamiltonian operator. So in three ways we can represent Schrodinger wave equation, right? Next, coming to see hydrogen atom and Schrodinger equation. Discussing about hydrogen atom and Schrodinger equation. So when Schrodinger wave equation is solved, when it is solved for hydrogen atom, so when we are solving for hydrogen atom, there are some solutions obtained. Solutions obtained. What does that solution obtained when it is solved for hydrogen atom give? Solution, when you look into solution, it gives the possible energy levels the electron can occupy. See, around the nucleus, there are some energy levels. These are energy levels, not orbits. Energy levels the electron can occupy. So these are the energy levels in which the electron can occupy. Electron can occupy, and the solution also gives the corresponding wave function of electron. One thing, what does it give? It gives possible energy levels the electron can occupy. So what is given this solution when Schrodinger wave equation is solved for hydrogen atom? We get solution. That solution gives this information. What information? What are those possible energy levels the electron can occupy? Second thing is, and also the corresponding wave function of electron associated with each energy level. Wave function of the electron with each energy level. So when you look into the solution solved for hydrogen atom, when this Schrodinger wave equation is solved for hydrogen atom, we get solution. That solution gives information about these two. Okay, what is that? Possible energy levels the electron can occupy and wave function of the electron with each energy level. Right? See, solutions of this equation provide several values of psi, including imaginary values. Including what? Imaginary values. So if you look into the solutions of this Schrodinger wave equation, it provides several values of psi. The solution contains several values of psi. Already we have studied wave function of each electron. Wave function means psi. We got psi values. And in those psi values, we have psi values which are valid and which are not valid also. Okay, imaginary values which are not valid as also we got. See, valid psi values. How can we identify valid psi values? Only those values of psi are valid which satisfy the following conditions. What are those conditions? One, the wave function must be finite and continuous. So we got the psi values. Some are valid psi values and some are not valid psi values. Which psi values are valid and which psi values are not valid? There are some conditions by which we can identify that some of the psi values are valid psi values. What are those conditions? The first condition is that psi must be finite value, and it should be a continuous one. The second one is the solution must be single valued, then only it will be valid one. Single valued is a single value. And the solution must be normalized, normal, and satisfy the relation. What is that relation? Integration 0 to infinity psi into dr is equal to 0. What does this represent? It represents that the probability of finding electron will be between 0 and infinity. It will not be present at the center of the nucleus. It will not be present at the infinity. It will be between these two. Then only the psi value is valid one. Okay. So this is nucleus and that is infinite position. So that is the condition. The solution must be normal one and should satisfy this relation. The next one is del psi by del x or del psi by del y and del psi by del z must be a continuous functions of x, y and z respectively. They must be continuous functions of x, y and z respectively. Then only if these four conditions are satisfied, then we take that solution as a psi, as a valid psi value. Valid psi value. So only those values of psi are valid which are satisfying these four conditions. Okay. Next, principal quantum number, azimuthal quantum number and magnetic quantum numbers are derived from the solutions of this Schrodinger equation. We have four quantum numbers. Among those, three quantum numbers are derived. Three quantum numbers are derived from Schrodinger wave equation. So we write in this way: psi n l m. From Schrodinger wave equation, we get psi values. For the psi value, we write n l m. For example, psi 3, 1. What does this represent? 3 is n value, 1 is l value. Okay. So what will be that orbital? So psi represents orbital. Psi represents atomic orbital. So what is that orbital? 3. For whom L value is equal to 1, p orbital. So 3p. If something like 0 is also given, then for which orbital we write 0 z orbital, 3pz. Like that. Psi 4 to, if in this way, if it is given, then which orbital it will be? 4. For which orbital L value is equal to 2? D. So 4d orbital. Psi 2, 0. So 2. For which orbital L value is 0? S orbital. So 2s. So in this way, three quantum numbers are derived from the solutions of Schrodinger wave equation. And what are those? Principal quantum number, azimuthal and magnetic quantum number. Spin quantum number is not derived from the Schrodinger wave equation. Next, significance of psi. What is the significance of psi? So psi, already we have studied that it is called as wave function. It corresponds to energy state. Normally we have discussed that there are different energy states in which the electron can occupy, which contains all information about the electron. It corresponds to the energy state which contain all information about the electron. Which energy state? And that psi, if you write psi, that wave function contains all the information about the electron. So it is just a mathematical function whose value depends on the coordinates of the electron in an atom and does not carry any physical meaning. This is important. Does not carry any physical meaning. It is just a mathematical function. Psi is only a mathematical function. Such wave functions of hydrogen and hydrogen-like species with one electron are called as what? Atomic orbitals. So wave functions of hydrogen and hydrogen-like species containing one electron, those wave functions are called as what? Atomic orbital. So psi means it is just a wave function. It gives all the information about, it corresponds to energy state which contains all information about the electron. It is just a mathematical function whose value depends upon the coordinates of electron in an atom and does not carry any physical meaning. And those wave functions of hydrogen and or hydrogen-like species with one electron are called as atomic orbitals. Okay. Next, the energy of orbitals of hydrogen or hydrogen-like species, one electron species, depend only on one quantum number, and that is n. But energies of orbitals in multi-electron atoms depends upon quantum number n and l. So energies of orbitals of hydrogen or hydrogen-like species depend only on quantum number, one quantum number, and that is what? Principal quantum number. But energies of orbitals in multi-electron atoms containing more than one electron depend upon quantum numbers. Their energies depend upon two quantum numbers. What are those? N and L. So that is about Schrodinger wave equation. And let us see important features of quantum mechanical model. What are those important features of quantum mechanical model? Now only we have studied something about quantum mechanical model of atom. In this, both Schrodinger, de Broglie dual nature of matter, that is wave nature, and Heisenberg uncertainty principle, both are taken into the consideration and explained. So what are those important features? It states that energy of electron in an atom is quantized. So every electron in a particular energy level has a specific amount of energy. Quantization means can only have certain specific values. So these are different energy levels. These are not paths, these are energy levels. Now only we have spoken about energy levels. So energy of electron in that energy level is possessing some energy. Electron in the energy level possesses some energy, and that energy in that specific energy level is quantized. Quantization means having some specific values is called as a quantization. So electron in a specific energy level possesses some specific energy, that is called as a quantization. It explains the probability of finding the electron around the nucleus in 3 dimensions. So quantum mechanical model describes about only the probability of finding electron, because as said in Bohr's atomic model that there is definite path. From Heisenberg uncertainty principle, it is found that there is no definite path. When there is no definite path, then we have to speak about only the probability. So quantum mechanical model describes about the probability of finding electron around the nucleus in 3 dimensions. So an atomic orbital is simply wave function for an electron. So wave function describes about, or wave function is nothing but an atomic orbital. So as psi is having both the positive and the negative, we cannot describe psi in the terms of probability, because psi is having both values. What are both values? Psi is having positive and negative. I cannot discuss the probability of finding electron in the terms of psi, because here it is positive, but here it is negative. Positive probability, negative probability is not possible. Okay, zero probability is possible, but negative probability is not possible. So for that purpose, what is done? Psi is, we are squaring the psi. When you are squaring the psi, positive into positive gives positive. Okay, negative, if there is negative, negative square gives you positive. Or otherwise, we also write the mod of psi square. This is, in this way also we can represent. So what is this called as probability? Probability density. What is that called as a probability density? So probability density is always positive, cannot be negative, and it indicates maximum probability of finding an electron at a certain region around the nucleus in an atom. So probability density describes about the probability of finding electron. See, here is a region. At this region, the probability of finding electron at this region is described as probability density. So probability density means it is the probability of finding an electron at a certain region around the nucleus in an atom. And the probability of finding an electron at a certain distance from the nucleus. See, from the nucleus at a certain distance. At what distance this electron is present is discussed by what? Radial probability, and that is called as radial probability. So radial probability, what is meant by radial probability? It is the probability of finding an electron at a certain distance from the nucleus. From the nucleus at a certain distance. At what distance the electron is possibly to be present. That's called as probability of finding the electron. And that's called as what? Radial probability. We can also say it as radial probability function. So radial probability is given by an expression 4 pi r square psi square. 4 pi r square psi square. How can we discuss this? See, let us take this as center of the nucleus. Considering this atom as a spherical shell, and the radius of this spherical shell is r, and in a thickness of dr, this probability of finding electron is present. Thickness of dr, the probability of finding electron is present. So for a spherical shell, what will be the area of that spherical shell? 4 pi r square, and volume will be area into thickness. In what volume? In this volume, there is probability of finding electron. Okay, then volume will be area into thickness 4 pi r square dr. So radial probability is given by 4 pi r square psi square. 4 pi r square psi square is given by this radial probability. So radial probability means at what distance from the center of the nucleus the probability of finding electron is present. Okay, that's called as what? Radial probability. So in the next session we will be discussing graphs, how the graphs are obtained when you plot the graph between radial probability and the distance from the nucleus, and when you plot a graph between psi and distance from the nucleus, psi square and distance from the nucleus we will discuss. So we shall meet in the next session with the radial probability distribution curves. Okay. Thank you for watching.